Hello everyone, in this chapter we are going to talk about TCP/IP networking. So this is just a recap of what we have done in this semester. So in the first 4 chapters we have looked at an overview of networking, some of the core concepts, and then we look at network security. And then chapter 5 is about the wired Ethernet, while chapter 6 and 7 are about wireless networks. So if you look at chapter 5 to 7, they are basically on layers 1 and 2. And then in this chapter and the next chapter, we are going to talk about the internet, with the TCP/IP, and also other related protocols that we use to connect computers in different signal networks together to form the big internet. So these are layers 3 and 4. And then in chapter 10, we'll also talk about the wide area networks. We actually cover layers 1 to 4. So we will talk about the different protocols and standards used to support wide area networks at the different layers. And then if you have time for chapter 5, then it will be about applications, that will be layer 5. So these layers 3 and 4 will be the focus of these 2 chapters. So we'll first have a quick recap of the TCP/IP concepts, and then we'll look at the IP address, and also we'll look at how the hierarchy of IP addresses can be seen in the address. And then we'll look at how routers operate in the networking, and then we'll look at the protocol called the address resolution protocol. And then we'll also look at the difference between IP version 4 and IPE version 6. And finally, we'll talk about TCP and UDP again with a little bit more details than we did in previous chapters. So in earlier chapters, we talked about layers 1 and 2, which are the physical and data link. So the standards in those layers come almost entirely from OSI. And then in this chapter and the next chapter, we are going to talk about the internet that operate at layers 3 and layer 4. So it's the internet layer and the transport layer. The standards come predominantly from the Internet Engineering Task Force. So it's basically not from OSI, it's from IETF. So they are called the TCP/IP standards. So the publications are called the request for comments. So again, I think we mentioned in earlier chapters, although it's called request for comments, that sounds not like a final document, but many of these RFCs are actually the final standard. So here are the major TCP/IP standards. So in layer 3, so the internet layer, that is mainly just the internet protocol, IP. And then you have some other kind of supervisory applications that are kind of to facilitate the running of IP. So it's like you have ICMP and ARP, like address resolution protocol, that you can help the operations of IP. ICMP is for the control and management. And then layer 4, then predominantly it was TCP, especially in the very beginning. But then people find that there are some limitations, or there are too much overhead with TCP. So that's why we have some people who came up with UDP, which is the user datagram protocol. So that is also widely used for applications that do not require high reliability. So that's why these are the major protocols in these 2 layers. So we don't have too many other protocols in these 2 layers. So basically these are the major standards that we are using. So TCP and UDP are for transport. But this one, you say like these 2 are not really like supervisory applications like what we are putting here, right? I think it's only mostly for like layer 5. But then if you think about it, for layer 3, then it's also kind of like that these are like helping. But then TCP and UDP are not kind of classified that way, so just be careful. So this table is not presented very well. Okay, so TCP/IP also has many application standards that you can build on top. Like in the application layer, then many user applications like HTTP for web pages and SMTP for emails, or of course there are many other applications that we can use on the internet. And there are also supervisory applications like DNS, that is for dynamic routing, for domain name service that we talked about in earlier chapters. Also, we have dynamic routing protocols and also many other protocols that are kind of helping the operations of the internet. And the ICMP and ARP are also supervisory standards. So as we mentioned, UDP actually is not, so this diagram is not, this table is not presented very well in that sense. So UDP, TCP are basically for for your transport, but not like ICMP and ARP that are mostly to support the transport of IP. Then we're going to talk about the hierarchical IP addresses. So in IP version 4 address, usually there's one part that is the network part, and then the next part is the subnet part, and then you have the host part, and the total always is 32 bits. But then for the network part, subnet part, and host part, there is no fixed length. So although in this example, like we may think that this one is the network part, 16 bits, and then this one subnet part 8 bits, host part 8 bits. So that's one possible configuration, but it's not always the case. So an IP version 4 address usually has 3 parts, but you cannot tell easily which one is the first part, which one is the second part, and so on. So the meaning of the parts are like this. For example, in this case, 128 .171. This one is actually the network for the University of Hawaii, right? So that means every host or every IP address within this network should start with 128.171. And then this one is a subnet for the college. So Schindler subnet is 17. So it's this part here. So of course there may be another school, science school, then they have another subnet, another administrative department, then they have another subnet number. And then under that subnet, then they have like multiple computers or devices that are connected, and then each of them can be given like a different number for the host part. Right. So that's why if you are following this, then you can see easily like if an address start with this, say 128.171.17, then you know it is from the Schindler subnet under the UH network. So the network part is given to a firm, an ISP, or other entity like a university by a registered number provider. So the firm divides the address space into subnets. Then on each subnet, the host part indicates a particular host. So that means usually the organization can decide how you can divide the different numbers to the subnets. Right? So we'll talk more about that later. So just a quick question first. In an IPv4 address, how long are the network, subnet, and the host paths? Is it like 16 bits, 8 bits, 8 bits? Actually, as we said earlier, the answer is we don't know. So it can vary depending on the registered number authority and also the organization that is dividing the network part, the given network address into subnets. Then now let's talk about border router, internal router, networks, and subnets. So what do they do? So border routers actually connect different networks. So that means it's a router that is connecting one network to the ISP, right? Or sometimes it's connected to other networks. So this one is like within your, say, organization network. Then you may have some internal router. Then everything like within this network, say your corporate network, start with this IP address 192.168.x.x, right? So then border router is basically going out of your organization, out of your organization network. Then it will connect to other networks, say your ISP network. Right? So that's again the internet part, how you can go out of your own network and connect to the web and to the server of other companies. An internal router is one that connects your different subnets within the network. So for example here, this one is within your organization network. Then you may need to have a router that will connect the different subnets. Right, this one is connected to subnet 192.168.2.x. And this one is like 192.168.3.x. And so these are different subnets like within your corporate network. Then you have your internal router. But then this one like connecting your internal network to the external network and also like to ISP. And this one is called the border router. Okay, so there's actually no way to tell by looking at an IP version 4 address the sizes of the network, subnet, and host part individually. You only know that the total is 32 bits, but you do not know which part is the network. So that actually creates a problem for the routing. So the solution is we need to tell people how long is the network part, how long is the subnet part. And we do this by using mask. So say in spray painting, you often use a smart like a stencil like this, right? In this diagram, right? You try to paint something on the ground, then you actually have a mask like this, and then you can spray on it, and then later on, then you remove this mask, then you have the remaining image that you want to paint on the ground. So the mask actually allows part of the paint through, but stop the rest from going through. So now when subnet mask actually do something similar, we only let the first part of your IP address go through. We only keep the first part, and then we convert all the remaining parts or the remaining bits to zeros. So a mask actually is a series of initial ones followed by a series of zeros for a total of 32 bits. For example, I can have 16 ones followed by 16 zeros. Then your mask is like this. You have 16 ones, and then you have 16 zeros. So 8 ones is 255. You will use the decimal notation, and of course 8 zeros then is still 0. So then in the dotted decimal notation, so this one is 255.255.0.0. So it's the same mask here. Right. So that's why a lot of times when you connect to the internet, like through your ISP, sometimes you may need to set up this yourself. Although a lot of time actually it can be automatically captured, but sometimes you have to specify the mask or subnet mask that you are using. If that's the case, then you have to type these yourself, right? And then there's also another way to write it is just we call it the prefix notation. We just put /16, so that represent the number of initial ones. So because this one starts with 16 ones, so we can use /16. So in other words, that is actually saying the network part is 16 bits. Then we use say /16 or 16 ones like this. So that's the mask. Alright, just another example. So if I have 22 ones followed by 8 zeros, then the mask will be like this. Then if you convert to decimal notation, that is 255.255.255.0. And then in prefix notation, it will be /24. Alright, so just a little exercise. So let's just try to draw 32 bits of the mask /14. So do not do it in dotted decimal notation, just write the bits in groups. And so then of course what you would do is you have 8 ones here, right? And then 2 more ones, so it's 10. So you just have 4 more ones. 1, 1, 1, 1, and then 0, 0. And then followed by 8 zeros and then 8 more zeros. Right? And then of course if you want to convert to dotted decimal notation, what would that be? So the first 8 bits will be 255. And this one you have 6 ones, right? So, and then you have two zeros. The value of the final two zero actually is 3, right? 1 plus 2. So this one actually will become 255 minus 3, so it's 252, and then 0, 0. So the dotted decimal notation actually is 255.252.0.0 for this one. So masks are applied to a 32-bit IP version for addresses. When we apply a mask, we use what we call an AND operation. That means if the IP address say is 1010 and the mask is 1100, so for simplicity we just use 4 bits, right? So it's to make it short. So this one is 1100, so the result actually will be 1000. So that means if the mask bit is 0 like this, then the result is always 0, right? Because it's an operation. 0 and 0 is 0. 1 and 0, like true and false. Then the answer is also false. This one is false and true. Then the result is also false. And then true and true, then the resulting bit will also be true. So that's the bitwise AND operation. So for those of you who have done some programming, you will know what that means, right? So just for every bit you do an operation, and then if both of them are 1, then it becomes 1. If the mask bit is 1, but if this one is 0, then it will still be 0, right? But if the mask is 0, then the answer must be 0. So basically what it's doing is, for this part, like the initial part, your result will be exactly the same as your IP address, right? But then for the 0 part, then the result will always be 0. So in other words, you are just getting the initial part of your IP address. Then if this initial part is the network part, then when you apply this mask to your IP address, then you are getting the network part of your IP address. So that's how the mask works here. So just another example, looking at say destination IP address is 128.171.17.13. So if the network mask is /16, so that means I'm just going to have 16 ones followed by 16 zeros. So the first 16 bits are 1, so it's 255.255, and then .0.0. Then what we are getting is, because these are all ones, so when you apply these to your IP address, you just get the network part of this IP address. You get the same value for this part for the IP address. So this one will still be 128.171, and these will all still be zeros, because they are all zeros. When you apply these to the IP address, they will all become 0. So the good thing about using mask and bitwise operation is, this kind of bitwise operation is much faster. Like compare with if you write a little, say, if then else statement saying you just, or like even a for loop, you just say if you have 16 bits, then you just copy it bit by bit, then of course it will be very slow. Then bitwise operation is fast, so that's why mask is used this way. So another example, so the same IP address, but this time the subnet mask is /24. So then I have 255.255.255.0. Then the result of the master IP address, which is actually basically the subnet part of this IP address, in this case 128.171.17.0. So the last part here will become 0. Okay, so now let's look at router operation in more details. So we have talked about routers since chapter 1, so now we'll finally see what they do. We'll see what happens after a packet addressed to a particular IP address arrives at the router. And first, we'll recap the simpler way in which Ethernet switches handle arriving frames. Remember, they are very similar, but Ethernet is basically at the level 2 when you handle the frame, but then a router are handling the packets at level 3. So we'll first recap what we do at the Ethernet level. So remember, in Ethernet we have this switching. So Ethernet switches are organized in a hierarchy. So there's only one possible port to send a frame out. So only one row per address. And remember, they are in hierarchy like this. So you have a top switch here, right? This one is lower level. So you can only just go up to like different level of switches like this. Right, so they are in hierarchy. So and then remember, for each switch we have a switching table. So suppose this one is the switching table for switch 1, then we know if the destination is going to this E5BB computer, then the port is 5. So I know I'm just going to send out from port 5, right? And then you go to port 3 on switch 2. So it must be in a hierarchy. So for router, basically we don't have hierarchy. So routers are arranged in matches with multiple alternative routes. So that's also why we are saying, like in the internet, they are not like centralized with a top level router like that. So basically they are not in hierarchy. So that means it's actually possible for you to send a packet from host A to host B through multiple different paths. Yeah, so a router actually may also send a packet out more than one interface or one port and still get the packet to the destination host. In the diagram here, for example, from router A, if I send a packet out from this say interface 2, then you go to router C, then router C can send it to router E, and then router E will send it to this host. But then I can also possibly send it out from interface 1, then you will go to router B, then which will go to router D, and then go to router E, and then go here, right? So both routes actually are possible. So then actually the router will try to decide which route is better. So each route will have a routing table like this. Say you say this one is the route number 1, then it will go to the IP address range like this. So because we just need to know the range first. Otherwise, if you imagine if you need to store all the IP addresses in your routing table, it won't be possible, right? There are so many IP addresses. So that's why usually you store a range like this, 60.3.x.x. So that means anything with any IP addresses starting with 60.3, or in other words that are in this network, will follow this rule here. And here this rule is the packet will be sent out at port 1, and the next hop router is B. So that means the next router, the name is router B. Okay. So you can also have another rule like this, saying the IP address range is 60.3.47.x. So in this case, you are not going to just the network 60.3. I'm going to the subnet. I know a router can connect directly to the subnet like this. And if I do this, I should send out from port 2, and then the next hop router is C. So that means I'm actually having 2 possible routes here that can send my packet from router A to the destination. So in your routing tables, actually multiple rows may give conflicting information about what to do with a packet. So in this case, then later on we'll talk about how your router will decide which one to choose. Okay, so the routing process is that the router will process an individual packet and pass it on its way. Yeah, so usually we call this routing. Right, so IP routing is like what we have discussed. So you are given an IP address, then the router, like based on the routing table, we have to decide where to send this packet to. Then as we said, each router will have a routing table like this. So each row represents a route for a range of IP addresses. So often packets going to the same network or the same subnet, right? So you have a range of IP address which is different from your Ethernet like switching table. Your switching table, you have a specific host name, because normally within an Ethernet is smaller. Like, so you know the address of each individual host. But then for, as we said, for the internet, there are so many devices, you cannot possibly store all the IP addresses, so only store the range in your routing table. So Ethernet switching table roles are rules for handling individual Ethernet EUI-48 addresses. So again, it's individual specific host. And then in router, the routing table roles are rules for handling ranges of IP addresses. So these are the major differences between these two. So in the routing table, usually we will have the following columns or attributes. So first is the row number. So it designates the row in the routing table. And the second one is routing destination, is the range of IP addresses covered by the row. So the range of IP addresses that fall into this row. And the mask, that is the mask for that row. So if you are saying um, like what given IP address, then how many bits of this IP address are relevant, right? So, or how long is this subnet mask, right? So you can provide this. Actually, you have to provide this in your routing table, and this mask will be applied to your destination host address, and then compare with your range that is given here. And then you also have a metric, that is the quality of the route listed in this row. So it may be measured in terms of time or other costs. Now, of course, if it's in terms of the time or speed, then the less time is spent will be better, right? And then the interface is basically to use, basically is the port that you use to send the packet out. And the next hop router is a device, which could be a router or a destination host on the interface subnet to receive the packet, so you know who you are sending to next. So this one is an example of a simple routing table. So it's a row 1, 2, 3, 4, 5, 6, 7, 8, and so on. Then you have destination network or subnet. Right, so this one is basically the range of IP addresses that you want to cover for this row. And then here you specify how long is your mask here. So in this case, 16 bits, and the cost for this path is 47. So if they use the cost, that means I want to have a lower cost, right? And then also for time, I want to have a shorter time, right? So you need to look at what is the metric being used here. And the interface is say 2, and next hop router is G. So that means if I have an IP address that fall into this range, after applying the mask, then I will send it to port 2. And then you can also have like another rule saying like if the destination is this 172.30.33.0, then this one actually is local. Then I just send it out to interface 1, and this one is a local host, or it could be local router. And so this one is the third destination network or subnet here. And then this one is again you have the range, and then you have the cost, interface, and also the next hop router, and so on. So you can list out all your rules here in your routing table. So this one is just a continuation of the previous slides. We have more rows of this example. So the last row here is, that means anything else, right? 0.0.0.0. And then the mask is basically 0 bits. In this case, if you do not, basically if the addresses are not here, so it's not going to have any match here, then it's just going to send it out to interface 3, and we'll let router H to handle this. Now we'll talk a little bit more about the routing process. So wherever a packet arrives at the router will look at its IP address, and then there will be 3 steps. So step 1 is to find all the row that matches this IP address. And then step 2 is to find the best match row out of all these matches. And step 3 is to send the packet out according to the directions in the best match row. So step 1, the router will look at the destination IP address in the packet, and then it will match this IP address against each row. So first it will of course apply the mask to this IP address, and then it will see whether it's matching with any of the row. So we'll begin with the first row, and then we'll look at every subsequent row. So even if you find a match, you still have to continue. It will only stop after it looks at the last row. Even after finding a match, it will still go until the last row. So, for example, each row is a rule for routing packets within a range of IP addresses. Then the IP address range is indicated by a destination and a mask, right, like this. So this one is a range of IP address for row number 1, and then the mask is 16 bits. So that means I'm going to look at only the first 16 bits of the IP address, and then to compare the first 16 bits with these 16 bits and see whether they are the same. Right, of course, for second row, then there's 24 bits, and then we'll compare with these first 24 bits here. So again, each row is a rule for routing packets within a range of IP addresses. It's not one single IP address. So example 1 here, a destination IP address that is not in the range of the row. Okay, so suppose the destination IP address of the packet is this 60.43.7.8. And then first we apply the network mask that is on that row. Right, so it's the first 16 bits. Then after masking, you have 60.43.0.0. And then you compare that with the destination column value, which is got the range of IP address 128.171.0.0. So in this case, then there is not a match, right? Then you go to the next row, right? Okay, so now let's look at another example. So in this case, the destination IP address of the packet is 128.171.17.13. So we want to send the packet here. So first we apply the network mask to 55.255.0.0. And the result of masking is the first 16 bits of your IP address. So it's 128.171.0.0. And this one is the range of IP address in your routing table. So it's also the same 128.171.0.0. So in this case, this one is a match, right? So this one is just kind of like giving your conclusion. So in this case, it's a match. So that's why we'll keep this as one of the possible routes. And then the router will actually do step 1. We do this to all the rows because there may be multiple matches. So just two quick questions here. If there are like 127,000 rows and the only rows that match are the second and seventh rows, what row will the router examine first? So the answer is actually row 1. Actually, it doesn't matter how many rows are there, it will always examine row 1 first, and then we'll go to row 2, row 3, and row 4. Okay, and question 2, if there are, again, 127,000 rows and the only rows that match are the second and seventh rows, so to say, how many rows will the router have to check to see if they match? So will it stop at 2 rows or will it stop at 7 rows? The answer is no matter how many matches are there, the router will always go through all these 127,000 rows to see how many matches are there. Okay, so now we'll talk more about step 2. After finding all the row matches, then we'll find out of all these matches which one is the best match. So to find the best match, the router will use the mask column and also the metric column. Like this. Remember we said there is a metric that can be based on speed or cost or time, right? And most importantly, though, it will look at the mask first. So the router will examine the matching rows defined in step 1 to find the best match row. The basic rule is that it will select the row with the longest match. So that means the initial ones in the row mask. So say for example, row 99 has a match, the mask is 16 bits. And row 78 also has a match, the mask is 24 bits. So then row 78 is the best match row. Because it's actually more specific, right? You can guess here, like it's actually sending it directly to the subnet. But then here, actually, this one is only sending to the network. You still have to find the subnet within the network. So this one is more specific. So it's kind of like when you try to mail a letter, if they say you will find there's a route to mail it to Hong Kong, then it's okay, right? But it's not very specific, right? But then you find another route that actually will send it directly to say Causeway Bay, Hong Kong, then it's better, right? You already arrive at the subnet part. So that's why when we do the matching, you will go to the part that has a longer match in terms of the mask. Right? Okay, so how about if there is a tie? So if there is a tie for longest match, then we'll select the rows based on the metric. Right? So say for example, there is a tie for longest match in this example. Say row 668 has a match length of 16 and the cost metric is 20. So row 790 has the match length also of 16, but the cost metric is 16. So we would like to select the row with a lower cost. So then in this case you select row 790 because it has the lowest cost. Then actually you have to look at how the metric is used. Sometimes it's not about cost. I will look at it in the next example. So in this case, there is also a tie. So row 668 has a match of 16 bits, but the speed metric is 20. And then this row 790 also has the same match of 16 bits, but the speed metric is 16. So in this case, the router will select row 668, which has the highest speed. So of course, you need to look at the meaning of the metric. Like of course, if it's specified in terms of speed, then a higher speed is better. If it's specified in terms of like cost or time, then the lower cost or shorter time is better. And say the following rows are matches. Just an example, you have like row 220, mass is 24, speed is 40, and then row 345, mass is 18, speed is 50. Then this one, the last one, mass is 8, speed is 40. So which one will we select? Okay, so the answer is actually row 220 because it has the longest mask, right? So we'll select this one. Then let's look at another example. So we have 4 rows here. The first one has a mask 12. This one has a mask 14. And then the third one has a mask length 18, and also the last one also has a mask length of 18. So we'll first select the two with the longest match, right? So in this case, row 345 and row 682, and then between these two, we'll select the one with the higher speed, right, with a better metric. So in this case, row 345 has a higher speed, right, 50 versus 40. So that's why in this example, row 345 will be selected because it has the longest match, and also among the two with the longest match, it has the highest speed. So one more example here. So we have 4 rows again. You have 4 different masks, and row 345 and row 682 has the longest match, 18. But then they have different cost metric. In this case, we select the one with the lower cost, right? So that means it will be 682 because it has the longest match, and then among the two with the longest match, it has a lower cost of 40. So the 682 will be the best match here. Okay, so now we'll look at step 3. So after deciding which row we should follow, then we'll just send the packet out according to the direction in this best match row. So if this best match row is saying like interface 5 and the next hop router is say A, then you will just send it out there. So you will send the packet out the interface specified in that row. So if row 1 the interface 2, next hop router is G, and so interface 1, next hop router is local, then you just send it based on the direction there. So if the destination says local, then actually the destination host is just out that interface. So you just send out that port, and then you send the packet to the destination IP address in the frame. So this is just a quick recap of the routing decision. So there are 3 steps. So step 1, the router will first find all the row matches by applying the mask and then just do the matching one by one. And then step 2, out of all the matching rows, then you will find the one with the best match based on the length of the mask and also the metric. And step 3, you will just send the packet out according to the direction in the best match row. So we'll talk a little bit more about this decision catching. So we have said consistently that the router must look at all the rows when it receive an incoming packet. So that's what should be done theoretically. So however, it is actually not true because when you do this for every packet, it will be very slow. Right? You will imagine you have like hundreds of thousands of rows in your routing table, and then you do it one by one. You go through all these rows one by one for every single packet, it will be very slow. So normally your routers may remember your decisions and put them in a list called a cache. And it could be like in a hash table like this. So you have a small cache that will store all the routing decisions that you have just used. Right. If an incoming destination IP address matches an IP address range in the cache, then you just use the same decision. Right. There's no point for you to look at the routing table like for every single packet, like going to the same destination. Right. So usually the caching is used. Of course, caching can be dangerous because the routers and also the transmission lines can come and go, but it can be very temporary and they can disappear just in a few minutes. So the best route to a destination host can also change very frequently, depending on again the traffic situation and also the whether the routers and the transmission lines are working or not. So a cache-based decision may be inefficient or even wrong. So when caching is done, usually the cached entries should be deleted very quickly after they are created. So normally maybe within several minutes, then if there's then you have to check again, or it will be just removed um, after they are created within a short time. Otherwise, like if you cache a kind of a line that is not working anymore, then you will not be able to connect to that destination anymore without updating your cached entries. Okay, so far all of the masks that we have seen have broken the network subnet and host part at the 8-bit boundaries, so because that's easier for us to illustrate our examples. Right. However, like mask paths actually often do not break at the 8-bit boundaries. So when we work with all these masks, actually, if you really want to figure the things out, it will be easier for you to work in binary, but not the decimal notation. So for example, if I have an IP address like this, like 3.143.12.12, if the mask is 255.248.0.0, then and also the destination value of the range of IP addresses in your routing table is 3.136.0.0, then is this a match? Then it's actually quite difficult for you to just see it from the numbers, like the decimal numbers. So you have to do it, you probably have to convert it to decimal and then do the matching, do the masking yourself, right? Do the bitwise and then see whether whether it match with the destination value. So we change it to binary to 3.14.3.12.12 to binary is actually this. Right? And then the mask 255.248.0.0. So 255 is this, right? 248, if we think about it, is 255 minus 7. So you just make the last 3 bits 0, right? 1, 2, and 4, right? They represent 1, 2, and 4, so the total is 7. So we make this 0, so that's 248. Right? And then the remaining are zeros. And then also the destination value 3.136.0.0, then it would be this, right? This would be 3. And then 136 is actually 128 plus 8, right? So this bit 128 is 1. This bit of 8 is also 1. And the others will be 0. So then this one, you will see this one will be your destination value. Then now if you just compare this, like if you do a math on this, right, if you look at the part here, and then it's the same as this, right, up to this one here. So in this case, this is a match. Right, so this one is just showing this more clearly. Right, so the IP address, when we apply the mask to the IP address, the result will be this. Because these are all the ones, then you just copy from above. And these are all zeros, then they just remain 0. Then this one will be the match with your destination range. So this one is a match. So you have to do it in binary. But of course, like in reality, like normally you should be doing all these in the program, right? Then you just apply your bitwise and then you just do a comparison. So now we'll look at something called the Address Resolution Protocol, ARP. So the problem is that the router wants to send a packet to a next hop router or to a destination host. So the router actually knows the IP address, but it must send the packet in a frame that is suitable for that subnet. Right? So I actually have to put my packet into a correct frame, but I do not know what frame you want to use for that subnet. So the router does not know the destination device's data link layer address. Right. So I do not know that address. So I must learn that address using the Address Resolution Protocol, ARP. Right. So that's why we need this Address Resolution Protocol, such that when I put it in the frame, I can also put your data link layer address. So normally it's like your UI48 address. So I need to know what to put there. In order to know the UI48 address of your next router, then you actually broadcast an ARP request message. So you just broadcast the message as in say IP host with this IP address. What is your UI48 address? So you broadcast this message, and then the host say which is not responsible, then does not respond to the ARP request. When this host is basically the one that is intended, then it will reply. So it will reply saying my UI48 address is this. Then the originating router will know, and then you can put this into the frame for that for the message to be sent. So that's why when you have this ARP, you can actually broadcast the message and ask about the UI48 address of your next hop router or your destination, such that you can put it into your frame header. So router places IP address on the DLL address pair in an ARP cache. Then you don't need to run ARP again for this same IP address. So again, like once you know this IP address, you can just put it in a cache, and then you know the UI48 address of this destination in the future. Then you don't need to ask it for every packet. So now we'll talk about IP version 4 and IP version 6. So this one is the header of an IP version 4 packet. So it's the dominant version of IP today. So the version number in the header is 4, right? 0100 in binary. So the header length and the total length fields tell the size of the packet. So this is the header length and this one is the total length here. And the DSCP, which is the differentiated surface control point field, can be used for quality of service labeling. So that's kind of the header the first row here for the IP version 4 packet with say 32 bits. And then the second row is used for reassembling fragmented IP addresses. But IP fragmentation actually is quite rare, so we will not look at this field in details. So supposedly you can do IP packet fragmentation, right? So and then you can use these bits to reorganize them, but it is not commonly used. Okay, and then if we look at the third row, the first part of the header here is actually the time to leave, so it's 8 bits. So the sender actually sends the time to leave value, which is usually 64 or 128 in the beginning. So each router along the way will decrease the value by 1. So that means after you go to the next router, then it becomes 63. Then if you go to the next router, then it becomes 62. Then it becomes 61, 60, and so on. So each router, as we said, it will decrease the value by 1. And then a router decreasing the value to 0 will discard the packet. Right? So if after 64 hops it is still not arriving the destination, then this packet will be dropped. It will not live on the network forever. Right? So it may also send ICMP error message to the sender. So the reason basically is this: like sometimes if you have some problems in your network, in your routing mechanism, then you may have some packets that may be like routing in circle on the internet forever. So that's why this mechanism will make sure that you can only go at most 64 or 128 hops. After that, you must disappear from the network if you still cannot arrive your destination. And then the protocol field describes the message in the data field. So like if it's 1 is ICMP, 6 is TCP, 17 is UDP, and so on. So it's actually specified whether it's using which of these protocols is used. And then there is also a header sum here. So as we saw in earlier chapters, the header checksum field is actually used to find errors in the IP packet header. So if the packet has an error, then the router will drop it. So as we say, that inner layer is what we call an unreliable protocol. So even if there is an error, there is no retransmission. So it will only be dropped, but we will not retransmit it again. So this unreliability will have to be handled at another layer. So normally at layer 4 by TCP. And then we have the source IP address, which is 32 bits, and also destination IP address, which is also 32 bits, as we have discussed before. And then we can also add options. Right. So these are rare and also indicate actually a malicious packet. So not these options are rarely used. But then of course the IP address is, as we said, 32 bits, and we know 32 bits actually that means you can have 2 to the power 32 possible values. In the beginning, so when people came up with IP many years ago, they thought like 32 bits would be more than enough. But now of course like people find that it's not enough, so that's why people came up with IP version 6, which we will discuss very soon. So as we said, IP version 4 allow more than 4 billion addresses, 2 to the power 32. Right. Actually, you can easily calculate 2 to the power 10 is how much? Is 1024, right? 2 to the power 20 is around 1000 times 1000, so it's 1 million. And then 2 to the power 30 is around 1 million times 1000, right? Because you multiply it by 10 more times, right? By 1000, so that would be 1 billion. And then 2 to the power 2 is 4, so that's around 4 billion, right? When you say 2 to the power 32. However, addresses are usually given out by the Internet Assigned Number Authority, the IANA, in chunks. So sometimes you give out a big chunk of IP addresses, again based on the network, right? I give you say 20.20. anything. I give it to this organization, and then you may not actually use all of these addresses. You may be only using half of it. You may be only be using 10% of it, right? Similarly, when I assign a subnet, say suppose within an organization, when I assign a subnet to a department, I assign a subnet with 24 bits, right? That means the remaining host part, you only have 200. You can actually have 256 different possible values. Like maybe in your department, you only have 20 devices, then you are only using those 20 IP addresses, right? You are wasting more than 200 IP addresses. So that's why many of these IP addresses actually are not used, right? So today, people actually estimated that only around 14% of the IP version 4 addresses are really in use, but we are already running out of IP addresses to assign to new organizations or new ISPs. So IP6, fortunately, has 128-bit addresses. So this is really an enormous address space, 2 to the power 128. So again, if we imagine 2 to the power 10 is 1,000, and then 2 to the power 20 is 1 million, 2 to the power 30 is 1 billion, 2 to the power 40 is 1 trillion. So this one actually 2 to the power 128, you can imagine it's like 1 trillion, right? And then times 256. Right, so that's a very large number, much larger than IP4. So it's supposed to be enough, right? So hopefully, I think it will be enough for even when we are doing like all the Internet of Things, whether you have all your wearable devices and so on. If they need or Internet of Things stuff, if they need an IP address, there should be enough. However, IP6 traffic is still relatively small compared with IP4. So of course, organizations must plan to support IP6 now because it's getting more and more popular. Of course, most of the networking devices or mobile phones and so on, they all not say all of it, but most of them would support like IP6, but of course most of them are also backward compatible with IP4, right? So of course, students would need a solid understanding of IP6, like if you are working in the field of networking. So IP4's addresses are written in dotted decimal notation, so we have looked at that before. We divide the 32-bit address into 4 8-bit segments, and then we convert each segment to a decimal number, and then we put the dots between the segments. So IP6 addresses are more complicated because they are longer, right? They are 128 bits. If you write in the dotted decimal notation, it will be like 4 times as long as your IP version 4 address, so it's quite long. So usually the IP addresses in version 6, they are written in hexadecimal. So you convert each 4 bits into hash symbol. So you write the letter symbols A to F in lowercase. And then you combine the 4 symbols into a segment. And then you separate the 4 symbol segments by colons. So in hexadecimal, like from 0 to 9, you still convert them to 0 to 9. But then it has the value of 10, that is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Right, so an IP6 address might look like this, 2001, 0027, FE56, and so on. There are also some rules to shorten this notation. So for example, leading zeros in each segment can be dropped. So for example, if my IP address is like this, and then this segment with leading zeros, I can drop these 2 zeros. Right? A segment with 4 zeros actually can also be dropped. All the zeros here can also be dropped. So this 0 can also be dropped. So in this case, if you are dropping all the leading zeros, then your IP address will become this. But of course, for 201, these zeros are not leading, so you cannot drop, because if you drop this, that will be very confusing. But then for this one, you know, right? 27 then can become 0027, right? So you just fill in the zeros, and then when you have two colons, consecutive colons like this, that means there are 4 zeros in between. So if there is a single set of consecutive segments that are all zeros, only the outer colons are kept. So if you have something like this, you can also change it just from 4 colons to 2 colons to make it even shorter. But personally, I don't like this one. I think this one is a little bit confusing because you only save 2 colons, but then there are some confusions that we'll talk about later on. Anyway, so you can shorten it like this. So the problem is sometimes when there is more than one consecutive group of segments that is all zeros, right? For example, it may be possible for you to have an IP address like this: 201 colon and then 4 zeros, 4 zeros, DFCA, 4 zeros, 4 zeros, 4 zeros. Then what you can do is, like, first we remove all these segments that are all zeros, right? You only leave the colons. So here you have 3 colons and then you have 4 colons. And then what you can further do is, for the longest segment here, you can just change it into 2 colons. Right? Then you can shorten it a little bit more. And then what if there is a tie for the longest group of all 0 segments? Then what you do is you only remove the inner colons from the first one. So when you have something like this, like 00, all zeros here, and these are all zeros here, what you do is, like, so this one you become, normally you become 3 colons, and this one you also only have 3 colons left. But then what you do is you can shorten this one to 2 colons. So this one is still 3 colons. So the reason for doing this is, for each of these IP version 6 address, we know there should be 8 segments, right? Because 128 divided by 8, then that will be 16, right? And then 16, so that means each segment has 16 bits. That's right, because for each number here, or for each has a decimal digit, like you have the value of 0 to 15, that's 4 bits, right? So each digit is 4 bits, and each segment is 16 bits. Okay, so there are 8 segments. So what you can do is you can always count how many segments are there, right? So you know there's 1 segment, 2 segment, 3 segment, 4 segment, and then here we know there are 2 0 segments, 5 segments, 6 segments. Then you can infer that there should also be 2 0 segments here, right? So that's how you can kind of infer how many segments are there after this simplification. But again, personally, I don't like this sort of simplification because it's not saving you a lot of space, but it's actually making the whole thing complicated. Yeah, I would rather leave all of them as colons, like just as many colons as there should be, rather than like removing some of the colons. But anyway, so some people would do this. So then we need to know. Alright, so just a recap of how we write our IP version 6 addresses. So we convert each group of 4 bits into a hex symbol, right? So we write the letter symbols in lowercase, and then we group the symbols into segments of 4. Right? So that's why we said each segment actually has 4 symbols, and each symbol has 4 bits. So that's why each segment has 16 bits. And then each IP address then will have 8 segments. That is 128 bits in total. And then you place the colons between each pair of segments. And then you remove the initial zeros in each segment. And then if there is a group of segments with all zeros, then you just remove the inner colons too. You can do that too. And you only do this to one segment, because if you do it to multiple segments, you do not know which segment actually is longer. So you only do it to the longest one. And then if there is a tie, you only do it to the first one. So that's how you convert, or how you convert your IP6 address from binary to hex symbol in writing. Okay, then we look a little bit more at the IP6 packet header. So of course the version field is 60110, and then it's followed by the traffic class. So it's the differentiated services field, which is kind of very similar to what we had in IP version 4. So you can specify the quality of service requested for this packet. So you can have different level, different classes of your packet. And the flow label actually is 20 bits. So it actually marks a packet as part of a specific flow of packets. So the flow label specifies that this packet is part of a flow of packets to be treated in a particular way defined at the start of the flow. So you can have a flow of packets instead of just having all the packets individually. And then you also have the payload length. So payload is actually the actual messages, actual data that you are going to send. So you are specifying the length of that part. So the header is always 40 octets or 40 bytes long. Then payload length is just the length of the remaining part. Okay, and this one is the hop limit. So it's basically the same as the time to leave. In IP version 4, but I think so the name is changed. The author of this textbook actually is saying the name change was done to confuse students. But personally, I think is actually there's also a good reason for that, because when you talk about time to live with the word time, people may think about whether it's really a time in milliseconds or something like that. But this one hop limit, then actually it might be more specific, talking about just how many hops you can go. Right, before this package should be discarded. But it's basically the same thing as time to live in IP4. And as we know, the source and destination addresses are now 128 bits long in IP6 instead of 32 bits long in IP4. So just a quick comparison of the two IP addresses. So IP4 then is 32 bits, then for IP6 128 bits, and the number of possible addresses. So this was 4 billion. This one, as we said, is 256 trillion. Right? So it's like this. Right. So we are running out of IP4 addresses, and then IP6 probably we still have a lot of addresses that we can use, and then some of the new devices actually only have IP6 addresses, but may not have IP4 addresses because we don't have that anymore. Okay, so where is all that fragmentation stop from IP4? So remember in IP6 we don't have the fragmentation anymore. So actually it's gone. So as we also said, IP packet fragmentation, although it's in IP4, but it's rarely done. So we don't do that. So when the packet is too big for a network along the way, actually it will be discarded. In IP4 it kind of will be handled, but in IP6 it was just too big that it will be discarded. So normally the sending host will first have to determine the what we call the MTU, the maximum transmission unit. That is the largest packet size along the route before transmission. So if you determine that before you send, then you just make sure that you don't exceed that limit, then you don't need any fragmentation along the way. And how about the header checksum? Remember in IP version 4, we have the checksum in the header to make sure there is no error. So again, IP6, because we want better efficiency. So this part is gone. So we don't do the checksum anymore. So if there's any error, we will let the transport layer worry about that. So this will avoid the work of error checking on each router along the way. You don't have to do the checksum calculation and error checking at every router. Then that will save a lot of time and computational cost. And then there is also a next header field in the IP6 header. So IP6 actually has many next headers. Each is linked to the next via the next header field. So actually, in addition to the kind of the standard header, you can have many different headers that you can use. So here, the next header, you can jump to the next header, right? So you tell what is the next header about, and then you can have multiple different types of headers within this IP6. So you may have something like this, your main header, then you say you have a next header, then you say this go to the you have the hop by hop options header, then you specify here, then after the main header, then you have the hop by hop options header, then you further specify that then the next header is the TCP segment header, then you can have this number to specify what header it is, then you jump to the next header. So the routers along the packets route typically only have to examine the hop by hop options header. So this will reduce the processing time per packet. So there are some other headers like routing header, like some others that are not shown here, like mobility header, and then the last one is no next header. So then you just stop there. So we have specified many different headers, but again, not every router not the router does not have to examine like all the headers for each packet one by one. Normally it's just the main header and maybe just a hop by hop options header. Then for the other header that may not be relevant, then it does not have to examine. Yeah, so this one is showing some of the common headers that may be used, like fragmentation header, authentication, encapsulation security protocol, destination options, and these are some mobility and no next header that we have mentioned. So we are not going into the details, but if you are interested, the good thing about all these network standards are they are all available online. So you can easily just go online and then read the specification, read the standards and the protocols and see what they are really about. And then you also have some upper layer messages header like TCP, UDP, and also ICMP v6. So this one is again the control protocol, but is an updated version for version 6 compared with the original one like ICMP version 4. So finally, in the last few slides, we will talk a little bit about TCP and UDP again. So we have talked about TCP and UDP in the earlier chapters. Is that the TCP actually receives an application message from the application layer process. And your application layer process again may be like based on HTTP or based on some other protocol for your application, right? And then you will need to fragment the application message into small segments, and then you send each segment in a separate IP packet. Right? So that's why we said for each message in the TCP layer, we call it a segment. So it will place a sequence number in each segment, and then the receiver will use these sequence numbers to reassemble the application message. So that means after getting all the segments may not arrive in order. I need to number each of them when I send, such that the receiver will use these numbers to reorder the segments into my original application message that I need. And also when the receiver receives a TCP segment correctly, it will need to send back the acknowledgement. This acknowledgement has an acknowledgement number that indicates which segment is being acknowledged. So that's a TCP process. So the other one is UDP. So UDP does not do the fragmentation. So there is a upper size of the upper limit on the size of a UDP segment. And sometimes we don't call it a segment, we call it a datagram, like for UDP. Like segment we usually use for TCP. So it does not need sequence number, acknowledgement numbers, or acknowledgement messages. So the good thing is this will be a very simple process. So I just throw the packet at you. Not the packet, I basically just throw the datagram at you. Of course, the datagram contains the packet, right? I just throw it at you. So the entire application message must fit into a single UDP datagram field, so which has a maximum size of 65,000 bytes. Right. So normally then you have to kind of handle this at your application level, how you are going to send the message with within 65,000 bytes. But the good thing is without all the acknowledgement, without the need to like reorder the thing and also sending acknowledgement messages, then this actually cut a lot of overhead, making UDP much more efficient and faster. But of course, the downside is not reliable. Right? When you miss a message, then there's no resending, there's no acknowledgement. You don't know as a sender when you send something out, you don't know whether the receiver has received it or not. So just remember, like for TCP, is actually quite cumbersome. Like when you need to do open a session, you need to have 3 steps. You need to do a thing, acknowledgement of the thing, and an acknowledgement of your acknowledgement. Right. And for UDP, you don't do that. You just throw the packet there. And also for TCP closing, it's like this. Like we say the 4-step closing. You say, alright, I'm going to hang up, and then you say okay, and then you say again, I also go to hang up too, and then this person say goodbye. Alright, so 4 steps closing. So again, I with all the acknowledgement and all these overhead, and TCP actually is a little bit slower. So of course, something that we did not mention in the earlier chapter is sometimes you also do a abrupt TCP close that will closes the connection immediately. Like RST is kind of like reset. Then the other side does not acknowledge. So that's one thing that we did not discuss in the earlier chapter, but something you can consider. So basically, this one is a quick comparison between TCP and UDP. Now, of course, which one is better? As we said, like TCP is better for reliability, and it's used in a lot of applications like web page browsing. Like when you use HTTP, it's basically based on TCP. But then for some other applications, then we want more on the speed. Like when you are, for example, streaming a video, right, or using some voice over IP, right, or having like online meetings, right. A lot of times you will miss some of the packets. Then actually you don't care. You don't need to go back and find that data anymore. Because it's not important anymore, right? And you are watching something like on live stream. Yeah, you don't need to get a message containing an image 10 seconds ago. You don't need that anymore. So for that kind of application, maybe you normally you use UDP, because it's faster. You don't have to have all the acknowledgement. Right? So that's why depending on different application, then you may have to choose which one to use, right? And a lot of time, of course, it's already specified in your application protocol that which one is better for that type of application. So that's the end of this chapter. So see you next time.